There you go. How's that? Now you guys can hear me? Thank you, Tom. Just started, so you guys didn't miss anything. So these are values that fall within a range or an interval. So no longer are we worried about the answer being specifically a discrete number. It can be anything in between. They're going to be measures of things versus counts, like we did on the last one. And they can be described by their density curves. And so we'll be focused on looking at those density curves and finding the area underneath within the range of intervals that we care about. So for those of you guys that don't know what density curves are, we're going to see pictures of them today, but they have an area exactly equal to 1 underneath it. So this part is in blue because it is very important for you to remember everything we do in probability equals up to 1. So when you see all these different distributions and all these different shapes, remember, if I were to calculate the entire area underneath it, it would equal 1. Okay, that's going to be helpful because we're going to be taking things away or using that to help us find different measurements that are readily available to us when we're using these distributions. And then they describe what proportions of observations fall within each range of values. So think of the depth of that area underneath the curve as sort of a reference to how much data is within that interval. All right, that's not going to be as important when you're going through these things, but just understand that's kind of what the picture is showing you. All right, it's not just pretty triangles and trapezoids just because we like shapes. All right, with unusual density curves, they can be of any shape. All right, we're not limited to just the ones we're going to show you, but these are going to be the ones that we focus on the most. All right, they are continuous, so that's why we're going to learn and study them in this particular unit. And again, our probabilities are going to be calculated by finding the particular area under whatever portion of the curve that we care about. All right, so before we start looking at the first couple of examples there on your notes, Skylar was helping us with this last class. I thought it'd be a good idea to write these down so you guys can copy them because they're not anywhere in your notes. They're not on your slides, but you could look them up on Google, I guess, if you wanted to. I wanted to give you guys the formulas that you might need for our main shapes that we're going to be discussing today for our distribution. So you might see triangles, which your formula is 1/2 of the base times the height of the triangle. You might use trapezoids, which is 1/2 of the base 1 plus base 2 times the height. And then rectangle / square is just base times height. Most of you guys probably know these. You probably remember them back whenever you got stuck in a geometry class. But in case you forgot or you don't want to go back and look it up or whatever, you can write these in that space in your notes kind of off to the right side next to all the words there, just a little bit of a space. And you can write those down. Remember that you can have this as reference later. So this will come in handy as we start to look at these weird, unusual distribution curves on the next couple of examples, and we start looking at the probability of different things. All right, so triangle, trapezoid, rectangle, those are going to be the 3 that you need to know. Don't worry about curved lines because that would require calculus. So there's no area of a circle that you got to worry about. No weird hexagonal shape. You can just use a triangle or trapezoid to figure it out there. Okay, if you need these again, I can put them back up as we wrap up the notes for today. All right, so how's this done mathematically? How are we going to find the area of the curve? We're going to do geometry. I mean, that's really what the next lesson here is going to be about. Can you do geometric formulas using information from a graph to find the area under the curve? And all of our areas are going to be less than 1, because remember, this represents probability. Okay, so you got to kind of put geometric concepts into the dimensions of statistics here. All right, so here's a random, unique density curve. All right, it looks like a triangle. So I want to find the probability that x is less than or equal to 2. So it helps if I shade these or have an idea of what portion of this triangle that I care about finding the area of underneath this curve. So I care about this red part right here for this particular problem. So this shaded area will change depending on what your probability statement is. So this represents all x values less than or equal to 2. Remember, this is continuous, so it's not just the 1 and the 2, it's everything in between now. So this is why we're looking at area and no longer just those discrete things like we did on our quiz. All right, so how do we find the area of a triangle? We just talked about this. It's 1/2 the base times the height. All right, so if I look here, all right, I'll draw it. It's easier for me this time not to be doing this on paper. I can just do it here. I have one length of the base here that's 2, so that's where this number comes from. And then I have one base here that has a height of 0.25, so that's where that comes from. All right, 1/2 of these is the same as dividing it by 2, so the probability is equal to the area under the curve, so the probability that x is less than or equal to 2 is 0.25. That's how it works, guys. You gotta get to do geometry again. How exciting. Some of you guys liked it, some of you guys hated it. Luckily, we're not doing proofs, so Connor don't have to worry about that. And you guys got thumbs up, Mr. G. All right, so will it be a little tricky on occasion to figure out the heights and widths of these? Yes, but if you use your mathematical number sense, you can find these. Okay, so there will be some examples where it's not going to land perfectly on the 0.25. It might land somewhere in here, but we can use our brains and how numbers work to figure out what the length of these bases are as we go through these examples. So kind of keep that in mind as we're doing it. It's not always going to be, perfect, but it'll be something we can calculate. Okay. All right, what if the question asks the probability of x being exactly equal to 2? Well, if I were to shade that, it would be something that looks something like this, to which I ask you the question, how do you find the area of a line? Any guesses? Is it even possible? Do you remember any formulas in geometry that said, here's the area of your line, go forth and find area? And the answer would that be no, because what if Sydney draws a really thick line, Connor draws kind of a medium line, and I draw a skinny line? How do we know which line is correct? Doesn't matter. There is no formula for the area of a line, so therefore you will never do equal to a number in continuous distributions. So the area here would be non-existent because there is no area for a line segment. This is one of our favorite trick questions to show and put in the quizzes and tests. Give you a continuous distribution and say, what's the probability x equals 2? And you just start plugging in things because you forgot x equaling 2 has no width. So therefore there's no area. So therefore there's no probability. Wait, Mr. G, can't they be just 2? Yes, if it's a discrete distribution, but this is continuous. So we're talking about intervals and there is no interval there. All right, so just be aware of that. There is no equals to 2. There's no special formula for the area of the line. It will always be 0 if it says equals something. All right, what about if the probability statement says x is just less than the 2? It doesn't have any equal on it. Well, the nice thing about continuous distributions is whether it says less than or equal to or just less than, it's going to be the exact same thing that we did earlier. Since lines themselves don't have any thickness, and since lines themselves don't have any area, then we don't have to worry about adding in the equals or not equals. It's going to be the exact same information. So it's still going to be 0.25 because you're still going to have, you're still going to have a length of 2 and you're still going to have a height of 0.25. You don't have to get all mathematical and be like, okay, I got to take the thickness of a line out, so it's really like 1.9999986 or something like that. No. Okay, there's no need to do that. Anything less than 2 is the same as less than or equal to 2 when it comes to continuous distributions, because the line is really non-existent anyways, which is hard for our brains because you see it, but just know as far as the area, it does not exist there. So whether or not you have statement number 1 in your notes or statement number 3, it's the exact same answer, exact same way it's done. All right, the other nice thing about continuous distributions is you can do things in between and to the right just as easily as you're doing stuff here. All right, so these are going to, again, be the same answer, x less than 2 and x less than or equal to 2, same thing, because there's no line thickness difference between those, exact same interval. Is this different than discrete distributions? Yes, because with discrete distributions, there's no space in between. So you're either at 2 or you're starting at 1. So that's what makes them different. With continuous, no difference here. We're okay with either one of these. If you write these down either way, you'll get the same answer. Now, you can do greater than or equal to on this one. Right? You just start at 3 and you go this way. And just start paying attention to what kind of shapes that you're dealing with here. So this one would be a trapezoid. All right, so I've got 2 bases going parallel here. So the one on the left and the one on the right are my bases. And then I have a straight perpendicular height right here between 3 and 4. So again, how do we find the missing lengths here of our bases? How do we find the height of our bases and how to do it? Well, we just use our number sense from the graph and we should be able to find things. So at 4, we can see that the distance for this base is going to be 0.5. They're on the same level. Okay, so no need to get a ruler out and measure the difference and say it's 4.9876. No, we're not doing that. So if it's here, it goes up to here, it's 0.5. Now, how do I figure out this one right here? Because it doesn't land anywhere specific. Well, if 2 goes to 0.25 and 4 goes to 0.5, then 3 is going to go halfway there. So all you got to do is figure out what this number is between 0.5 and 0.25. So if you add these up and divide by 2, you get the average. All right, so that number is going to show up on your screen here in just a second. So base number 1 is 0.5 because that's where it reaches to. Base number 2 is 0.375 because that's halfway between this one and this one, because 3 is halfway between this and this. That's how these things work. So don't try to overthink this and don't try to be too crazy with this, because you can make things way more difficult than you need to on this thing. I'm not going to throw one of those tricks at you and see if Connor can figure out that it's 0.4678999, you know, nothing like that. There's no point. Why are we doing that? All right, so I got my 2 bases. Again, the height on this one's actually going to be the range between 3 and 4. Remember from your geometry days, height is always perpendicular to bases. And then on a trapezoid, your bases have to be parallel. So if you try to measure this as your base, then you're not doing it right because it's not parallel to this one. So yes, you have to remember some of your basic geometric facts from 9th, 10th grade, whenever you took geometry. So now we can add these 2 things, multiply by 1, and then don't forget to divide by 2 or times it by 1/2 or however you want to do it. All right, so there's my formula. Half of 0.375 plus 0.5 times 1 gives me an area of 0.4375. Again, your answers should be decimal answers. Avoid the temptation to think that all area formulas have to come out to nice big 3-digit whole numbers with, you know, centimeters and meters and stuff on the end. That was geometry. We're doing probability, so everything should be between 0 and 1. We're just using geometry to find our answer. That's it. All right, what about if I have an interval? No bigs. You're just going to make your shaded area go between 1 and 3. All right, so my shaded area just shifts. Again, this looks like a trapezoid to me. So that's what I'm going to use as my reference here. We know the distance of this base is 0.375 from using it earlier. Again, how do I find the distance here? Well, whatever halfway between 0 and 0.25 is will be my distance. All right, that ends up being 0.125. So that's this base, 0.375. That's this base. And then my interval or my distance between those 2 bases is the height because it's perpendicular to it, and that's 2. So the formula again, half of the 2 bases added together times the height. So 50% of my data, or 50% likeliness or probability or whatever you want to say, is between 1 and 3. All right, so questions so far? And if you find this easy, then that's okay. It's okay to be easy once in a while with this stuff. If you don't find it easy, just remember, keep it simple. Look for just the links that you need, use the formulas that you need, and then don't add any more to it than that. Don't try to be so scientific that you're making things way harder on yourself than you need to be with these continuous distributions. There's no need for us to do that at this level. Does harder ones exist in the world? Absolutely, but there's no need for us to sit there and stress about it. All right, what if you got something weird and funky like this? Well, just kind of play with it and see what kind of shapes you get. You might have to combine different types of areas together. You may, we don't have a house formula. So you might have to do like a triangle and a trapezoid or a triangle and a square or whatever, okay? So you do have to do a little problem solving with this stuff. What do you say there, Skylar? What would you use, sir?
Well, I can make 2 shapes or 3 shapes.
I would suggest 2, though we don't have to do as much work. So which 2 would you pick?
There's a rectangle and a triangle.
Very good. Those are the same 2 that I picked. So if the probability that x is greater than 1 creates this weird house-looking shape. Again, there's no magical formula out there that says area of a house. All right. Yes, this is a polygon with 5 sides, but why do we want to do that to ourselves? We don't. So Skylar has it exactly right. You got a rectangle in here and you got a triangle. So treat them as 2 separate entities and add them together. So start with the triangle. We have a base of 2 and a height of 0.25. All right. So multiply those 2 together, divide by 2 or multiply by 1/2, however you like it. And so you have 0.25 as your area for the red triangle. Rectangles are nice and easy. It's just base times height. So I have a base of 2, and I have a height of 0.25. Multiply them together, that's 0.5. So what is the entire area of my distribution with x greater than 1.75? So like I said, if you need to get a little creative and add things together, I would. Don't try to make things more challenging than they need to be. We've got plenty of stuff that's difficult in life. When we do things like this, we can just do our thing. It's okay to be easy, like I say, once in a while. We've worked hard enough, we deserve it. All right, next one to look at is the probability of 0.5 to 1.5 for my distribution of x. So x is in between or greater than 0.5 and less than 1.5. All right, so I'm gonna have a little bit here and I'm gonna have a little bit here. So it's not gonna make, perfect shape, but if you watch them as they fill in there, there's kind of a rectangle there and a trapezoid there. So again, break it down into 2 separate shapes. You could also do a rectangle and then a little triangle here if you wanted to. I mean, it's entirely up to you guys. Again, don't work too hard though. Find the things that work best for you. So I chose these as 2 separate shapes, finding a rectangle like this and a trapezoid like this, because then I know these 2 bases here are gonna be the same, and I only gotta find this one here. All right, so for the first blue rectangle, it's gonna be 0.5, which is my height down here. I'm sorry, 0.5, yeah, and then 0.25, which is my base right here. So just multiply those together. So I get 0.125. And then for the trapezoid, all right, I know this is going to be 0.5 because it goes up into that point. I already know what this base is from earlier, 0.25. How do I figure this one out? It's halfway between these because 2 goes all the way to the top. So 3.75 there, just like before. Now I got my 2 separate answers, add them together, and I get 0.28125. If you round it to 4 decimals, which is perfectly fine, 0.2813 would be acceptable as well. Remember, don't round until the end though. So if you decide to round, only round this one. Do not round this one until after you've added it. Keep everything as accurate as possible. All right, so this is a gist of what we're going to do. I'm going to show you guys uniform real quick, which is just as easy because uniform is big squares and rectangles, nothing fancy. But this is the heart of the 2 lessons so far. So questions? All right, we'll probably have some time next class to work on this stuff in class. Don't leave yet because we got one more thing to show you, but just know that you can kind of start looking at this weekend if you want to experiment with it a little bit. How did I get the base? Which, this one here or this one here? This one?
Yeah.
So this length right here, this is base number 2. This length here is halfway between 0.5 and 0.25 because this mark here is halfway between 1 and 2. So if 2 is all the way to the top and 1 is only to right here, and I go halfway down, then I go halfway up. So 3.375 is that length here because that's halfway between these 2 numbers. This one here is 0.5 because it goes all the way to 1.5 and it stops at 1. All right, so some special continuous distributions. We're going to talk about both uniform and normal. Normal will be on Tuesday. Uniform fits with our geometric stuff. We're going to do uniform first. So with uniform distributions, it's again continuous that is evenly distributed amongst the graph. So your graph should look like a rectangle. There should be no, abnormalities going up or down or anything like that. It has a density curve in the shape of a rectangle. That's it. So if I roll a dice, that's a uniform, discrete uniform distribution, but something in that shape is what I'm looking for. Probabilities are calculated by finding the area under the curve. Well, it's a rectangle, so this should be fairly easy, Mr. G. How do you find the area of a rectangle? Base times height. That's it. Again, don't try to make this harder than it needs to be. Now, there's some space to write the formulas for the average and standard deviation of a uniform distribution. Notice we didn't talk about this with the other ones because you're not going to be worried about doing this with the other ones, just with this uniform one. So you're going to have an upper and lower value for your rectangle, where it starts and where it finishes. So if you take both of those numbers, add them together and divide by 2, you get the average or the middle mark of this distribution. This is where the 50% mark is going to be. It's uniform, so we know it's symmetrical. So where do we know the average is going to be? Right down the middle. Standard deviation is the largest number minus the smaller number, so I can keep everything positive, divided by the square root of 12. There's a reason why it's square root of 12. It's a nice calculus proof that we can talk about later. We're not going to do that today. So just know that it will always be the square root of 12. Those of you guys that are in calculus, I'll try to get the proof from Ms. Nichols. We can talk about it next class if you guys are interested. All right, your A and B, again, are the endpoints of your distribution. So A is going to be your lowest number, B is going to be your upper number. So if it goes from like 1 to 9, those are your endpoints. These are the two formulas. They're not written down anywhere else in your notes. So you're going to want to write these down. I have a piece of paper that has them on here too. I'll show you guys in a second. Because there's some other things that show up that aren't written down, so I'll give them to you all at the same time. All right, so the Citrus Sugar Company packs sugar in bags labeled 5 pounds. However, the packaging isn't perfect and the actual weights are uniformly distributed with a mean of 4.98 pounds and a range of 0.12 pounds. So I know where the middle number is on this distribution, and I know how far apart A and B are. So I'm going to use that information in a second to construct my diagram. Because I know a starting point. I start in the middle, and I just got to make sure the total distance between the ends is 0.12. All right, so I know it's going to be a rectangle. There it is. 4.98 is the middle because that's my average. And then between the upper and lower ranges, between A and B, needs to be 0.12. So if I cut that in half to figure out how far to the left I need to go and how far to the right I need to go, that's going to be 0.06. So if I take away 0.06 from here, I get 4.92. If I add 0.06 to this side, I get 5.04. Does that make sense? So I start in the middle, and I know that in between the ends has to be 0.12. So there's 0.06 on one side, 0.06 on the other side. It helps to draw these so that you can do these following questions. All right, how long is the rectangle? It has a range of 0.12. So then how am I going to figure out the height of this? Because I need to have the height in order to do the actual calculations. So here's your formulas. Average, standard deviation, we talked about that. A and B are your endpoints. The range is B minus A. Here's the formula for your height. Height is equal to 1 divided by the range. Always, 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 always. And here's the algebraic reason for why that works. If we know the area of the rectangle has to equal 1, and we know that the area of a rectangle is base times height or range times height or whatever word we want to use, and it tells me, hey, this is 0.12 is this range, then if I divide that away to get height by itself, it's always going to be 1 divided by R. So algebraically, no matter what, if I tell you the range is a number or you figure out what the range is, 1 divided by that is always your height. Every time, all the time. Because it algebraically has to work that way. Does that kind of make sense? Yeah. So if you want to write any of these things down, you can. I'll give you another minute to look at them, and then we're going to do this example, and then we'll save the second example for the warm-up when we come back on Tuesday. Because I got like 2 minutes. All right, so important, 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 important. Make sure you know all those things. They're not written specifically in your notes. So take a picture, watch the video later, whatever you need to do. Okay, so really quick, let's do a few examples, and then that example number 2 that says on your own. You guys can do that when we get back, either by yourself over the weekend or on Tuesday when we start class. All right, so again, my height is 1 divided by 0.12 based on the formula I have. So now I can ask the question, what is the probability that a randomly selected bag will weigh more than 4.97? So that's going to be somewhere down here in my shaded region, just shy of 4.98, and everything to the right. So how far apart are those two numbers, the 4.97 and the 5.04? Well, if you figure out what that distance is, right, which is 0.07, and you multiply it by the height, which is always going to be 1 divided by 0.12, you get your answer. Is the height ever going to change on this distribution? No, it's uniform. It's flat, consistent. Okay? So that's the nice thing. No fancy, weird triangles, trapezoids, just boop, make a rectangle. All right, for the next one, find the probability that a random selected bag weighs between 4.93 and 5.03. So again, kind of shade your region, get an idea of where you're working, and figure out how far apart are those two numbers. All right, to me, it looks like it's 0.1 apart from each other. So that's going to be my length. Again, does the height ever change on this? Nope. It's still 1 divided by 0.12. So I multiply those things. 83.33% of the data is between those two intervals. So I'm likely to find that many bags, percentage-wise, that weigh between that and that, if their original average and stuff is all accurate and true. Okay, so we're going to stop here because the bell's about to ring for us to do the pledge and all that stuff here in the next couple of minutes. You can start working on the first page of homework that has to deal with uniform because you've seen everything, and you can start looking at the unique, weird distributions with the triangles. When we get to class on Tuesday, we'll do example number 2 as a warm-up because we have a 3-day weekend this weekend. So if you didn't know, no school on Monday, which means that the next time I see you guys is Tuesday. So you're going to forget everything by then because you guys are high schoolers and you're supposed to do that stuff. And then we'll talk about normal distributions using z-scores and calculators and all that stuff. Again, reminding us what the empirical is. Which one? I know, and you're going to have to do it again. They're so exciting, fun, and useful. You do it every time. All right, Zoom people, have a good day. Thanks for taking the quiz, and we'll see you all on Tuesday. Enjoy your weekend. No, absolutely not. Is your name on it there, Miss Claire? Yes, it is. Thank you. Absolutely not, Miss Claire. You may not do that, even though I'm going to take it happily.
Well, remember the last one that
Yeah, I mean, so I know it's kind of weird and stressful that we're making you guys do the pictures, and I promise it's not my preference, but I just don't know what the AP exam people are going to do. Like, I don't. And they always play games until the last possible minute to tell us anything. And so I would rather us get through all the kinks and stress and practice now when we have time. Like right now, you can hand me the paper, you can still fix it. Because in May, if they go to digital for whatever reason, because now we got what, a new strain that we're all worried about, who knows, right? And so if they make everybody sit at home and take it again like they did last year, like it was very stressful for my students. We had not practiced it because we didn't know that was going to be the case. And I mean, over half of my students had to retake the exam again a second time. And that's just not, you don't want to spend the middle of your summer vacation, like June, 3rd week of June, 4th week of June, trying to remember what you've done all year because you've already shut things down because you couldn't simply get your work submitted to the raters in time. So I know it's not fun and it's the last thing you guys want to do. Trust me, I hate to do this too. But I want you guys as prepared as possible, especially now in the spring semester, because, you know, believe it or not, we're very close to the to the exam stuff here. So, because we're going to spend the whole month of April just, all right, what do you got? What do you got? What do you got? So Laura's going to hate class in April because we're going to make her do like 6 tests. It probably did. It's 10:58. You guys have a good day. Thank you there, Mr. Connor. You guys have a good weekend. Enjoy it because we don't have a lot of breaks.